This is the last day that we will be having adding anything to our notebooks for the year. So like I said, tomorrow we will have our review lesson, and then the rest of the year we'll be signing in for attendance, and you'll need to complete your online tests, your notebook check, and lastly, we've got the article assignment. Okay, so let's go ahead. Our questions for our video today are: number one, what element causes stars to die and why? Number two, how hot can neutron stars get? This is on page 20. And number three, what is a magnetar? Let's find out and get some details on that right now. Hold on. Okay, so I'm just going to play the first 6 minutes of this video here. Gets really in depth on some star stuff we're going to have on our test, and some really interesting stuff about neutron stars. Let's check it out. 3, 2, 1, 3, 2, 1.
Neutron stars are one of the most extreme and violent things in the universe. Giant atomic nuclei only a few kilometers in diameter, but as massive as stars. And they owe their existence to the death of something majestic. Stars exist because of a fragile balance. The mass of millions of billions of trillions of tons of hot plasma are being pulled inwards by gravity and squeeze material together with so much force that nuclei fuse. Hydrogen fuses into helium. This releases energy which pushes against gravity and tries to escape. As long as this balance exists, stars are pretty stable. Eventually, the hydrogen will be exhausted. Medium stars like our Sun go through a giant phase where they burn helium into carbon and oxygen before they eventually turn into white dwarfs. But in stars many times the mass of our Sun, things get interesting when the helium is exhausted. For a moment, the balance of pressure and radiation tips and gravity wins, squeezing the star tighter than before. The core burns hotter and faster, while the outer layers of the star swell by hundreds of times, fusing heavier and heavier elements. Carbon burns to neon in centuries, neon to oxygen in a year, oxygen to silicon in months, and silicon to iron in a day. And then, death. Iron is nuclear ash. It has no energy to give and cannot be fused. The fusion suddenly stops and the balance ends. Without the outward pressure from fusion, the core is crushed by the enormous weight of the star above it. What happens now is awesome and scary. Particles like electrons and protons really don't want to be near each other. But the pressure of the collapsing star is so great that electrons and protons fuse into neutrons, which then get squeezed together as tightly as in atomic nuclei. An iron ball the size of the Earth is squeezed into a ball of pure nuclear matter the size of a city. But not just the core, the whole star implodes, gravity pulling the outer layers in at 25% the speed of light. This implosion bounces off the iron core, producing a shock wave that explodes outwards and catapults the rest of the star into space. This is what we call a supernova explosion, and it will outshine entire galaxies. What remains of the star is now a neutron star. Its mass is around 1 million times the mass of the Earth, but compressed to an object about 25 kilometers wide. It's so dense that the mass of all living humans would fit into 1 cubic centimeter of neutron star matter. That's roughly 1 billion tons in a space the size of a sugar cube. Put another way, that's Mount Everest in a cup of coffee. From the outside, a neutron star is unbelievably extreme. Its gravity is the strongest outside black holes, and if it were any denser, it would become one. Light is bent around it, meaning you can see the front and parts of the back. Their surfaces reach 1 million degrees Celsius compared to a measly 6,000 degrees for our Sun. Okay, let's look inside a neutron star. Although these giant atomic nuclei are stars, in many ways they're also like planets with solid crusts over a liquid core. The crust is extremely hard. The outermost layers are made of iron left over from the supernova, squeezed together in a crystal lattice with a sea of electrons flowing through them. Going deeper, gravity squeezes nuclei closer together. We find fewer and fewer protons as most merge to neutrons, until we reach the base of the crust. Here, nuclei are squeezed together so hard that they start to touch. Protons and neutrons rearrange, making long cylinders or sheets, enormous nuclei with millions of protons and neutrons shaped like spaghetti and lasagna, which physicists call nuclear pasta. Nuclear pasta is so dense that it may be the strongest material in the universe, basically unbreakable. Lumps of pasta inside a neutron star can even make mountains, at most a few centimeters high, but many times as massive as the Himalayas. Eventually, beneath the pasta, we reach the core. We're not really sure what the properties of matter are when they're squeezed this hard. Protons and neutrons might dissolve into an ocean of quarks, a so-called quark-gluon plasma. Some of those quarks might turn into strange quarks, making a sort of strange matter with properties so extreme that we made a whole video about it. Or maybe they just stay protons and neutrons. No one knows for sure, and that's why we do science. That's all pretty heavy stuff, literally, so let's go back out into space. When neutron stars first collapse, they begin to spin very, very fast, like a ballerina pulling her arms in. Neutron stars are celestial ballerinas spinning many times per second. This creates pulses because their magnetic field creates a beam of radio waves which passes every time they spin. These radio pulsars are the best known type of neutron star, about 2,000 are known of in the Milky Way. These magnetic fields are the strongest in the universe, a quadrillion times stronger than Earth's after they're born. They're called magnetars until they calm down a little.
Okay.
But the
So
absolute
let's go ahead. Let's stop there because that's where kind of our last question was, number 3. But let's get back to that in a moment. Let's get to number 1 first. Angel, what element is going to cause stars to die? Iron, right? And iron's going to stop what process in the middle of that? What do we hydrogen and helium do what process to keep a star growing strong? Called nuclear what? Yes, perfect. Nuclear fusion. Remember, when we have iron stops nuclear fusion. It's kind of like it just stops the fusing. It's going to be like kind of like a dead battery. Okay, it's going to cause the star to die eventually. And then number 2, Angel, I think you saw this as well. How hot can a neutron star get? 1 million degrees Celsius, everybody. That is super hot, hence why it's blue, right? The sun's surface is only 6,000 degrees Celsius, but the neutron star, we're talking 1 million degrees Celsius, super hot. And the last one, if you didn't hear already, we talked about the magnetar. That is the magnetic field of a neutron star, but it is super powerful, and because of its spinning, it's going to spin a lot more than our magnetic field. So powerful spinning magnetic field. Powerful spinning magnetic field. Okay. All right. We're going to go ahead. I'm going to leave that up for a second. The table of contents is already up to date if you want to see that. We're going to have our last card question of your stars in our galaxy, the Milky Way. And parsec is used to measure like other galaxies and stars that are really far away. Okay, let's go ahead to finish out for the year. We're going to go back to page 15. Back to page 15. We have 3 stars to write about. 3 stars to write about really quick. So go ahead, go back to page 15, and we'll call it a day. No need to worry about that. Our first topic is the main sequence star. Okay, I'm going to give our in-person students a moment for that. Again, all we've got is 3 slides, and then we are done for the year. So I figured I might as well be quick about it. This is on page 15. We had 7 total stars, I believe, on that page that we never finished. So for main sequence, we have 3 more left, right? It's what our sun is, right? It's like the happy medium star, okay? So it's going to be a stable star from the nuclear fusion of hydrogen and helium, and it's got the gravitational forces equally pushing inward. So it's going to be pushing inside and going to make it a very solid, happy medium star. Okay. So you'll add that to page 15. We'll do the other two very briefly, and we'll call it a day. When everybody is ready. Again, this is the type of star. Our star is a yellow main sequence star. We're going to move on in about 5 to 10 seconds, everybody. So go ahead and take a picture if you like. All right. Let's now move on to our second to last star, which are the red/blue giants. I'm going to give our in-person students a moment here. This is our red/blue giants, second to last topic. So these stars, again, they're going to shine brighter, but they have a shorter lifespan, okay? And obviously, when a star becomes a giant, it's probably near the end of its life, okay? And usually causing supernovas, neutron stars, or black holes if they're supermassive. And the star core is going to run out of helium and get heavy and turn into like a dense metal, like iron, right? When it becomes that dense metal, the core gets dull and stops releasing energy, which eventually causes the star to dissipate or die. Our star, the sun, will actually become a red giant eventually, but it won't have enough energy or strength to make a neutron star or a black hole. It won't even have necessarily a supernova. It'll just kind of fizzle out and become a white dwarf. And then our last topic of the day, everyone, last one, then we're all done for the year. Neutron star. We just saw the video on that, right? Created when giant stars die, collapse in supernovas, and the core creates neutrons. We know all about that, right? They're the hottest stars. They have the strongest energy, the strongest magnetic field. They are some of the strongest, most fascinating stars in the universe. Go ahead. That is it for the day, everybody. Stay logged in, stay signed in, and take attendance one more time. Okay. Go ahead at this time. You should be working on catching up your notebooks, or you should be working on the article assignment. That includes 3 different articles. I'd say it should only take, there's only 5 total questions to answer. You can type those up and send those to me. Again, those are due before the end of next week. That is the last assignment of the year. Outside of that, the next few days, I will be finishing and posting the notebook check and the parts 1 and 2 of our last online test of the year. Again, all of next week will be a makeup. All of next week will be a makeup week. Okay? Give me one moment to take attendance.